Hello. So we will now start on assignment 2, which is on mostly electrostatics part, right? So and then stiction is also there. Okay. So the first question is that 4 particles, each with charge small q, are placed at corners of a square, and another charge capital Q of opposite sign is placed at the center of the square, and then the charges are such that the total force on each of those the total force on each of those 4 particles is 0. Then what relation is true? So for that we need to see that how the forces are acting. So let us say these are the 4 charges which are placed at the 4 corners of a square, and you in the middle there is a opposite charge. Now these charges, these small q charges, all are of same type, right? So they will repel each other. So let us assume any one charge like this charge, and this charge is repelled by this okay, let us name these corners A, B, C, D. So the charge present at A corner will be repelled by B, C and D, and if you see, so this like A to B, this repulsion force will act in this direction, right, and A to D will act in this direction, right. Now this force has 2 components, one component in this direction, another component in the perpendicular direction, right. Similarly this force also have 2 components, one component in exactly same direction and another component in the opposite direction. So these 2 components cancels each other, this and this cancels each other, and these 2 along the diagonal this component will add up. Now what is the force between them? What is the repulsion force? Repulsion force is, we know that 1 by 4 pi epsilon naught q square by r square, right. That is the formula. Now let us say that each of these arms, which are like a square, side is A, right. So and this 1 by 4 pi epsilon naught is equal to k. So it is k q square by A square. Now for the B and D it will be, so it will be ultimately this angle is 45 degree, right. So it will be 45 degree because this is along the diagonal, right. So total repulsive force is equal to 2 q square by A square cos 45 degree plus also the repulsion due to the C, right. If each arm is A, then the diagonal will be A root 2, right, because this is A square root of A square plus A square. So 2 q square by A square cos 45 degree is because of the charge present at B and D, and then because of the C the charge will be then q square by, the k also will be there, k q square by A square. So it is k q square by A square cos 45 degree, and because of both the B and D it is 2, 2 is multiplied, and then for C it is k q square by, it will be A root 2 square, A root 2 whole square, right. So this is the repulsive force, and the total force to be 0, the attractive force also have to be same, and attractive force is q. So the plus q charge is at this point, right, at the center, it's plus q, the opposite charge, whether it is plus or minus, opposite from the opposite in sign with respect to the small q charge. So q by, so this is half of the diagonal, the distance between the capital Q charge and small q charge at A is A by root 2 then k is there, so k will get cancelled, and if you equate it both the sides, then you will get that q equal to cos 45 degree plus 1/4 of small q, and that is equals to 0.96 of small q. So this is the correct answer using simple Coulomb's law. Next question is that consider a spherical charge distribution which has a constant charge density rho from r equal to 0 to r equal to a and is 0 beyond. Choose the correct pattern of electric field where r is less than a or its diameter and r is greater than a. Now let us say this is the sphere, and then radius is a, right, radius is a, so this is a, and it has a charge density of rho, inside. Now I suppose some of you have already done a mistake where you are thought about it like a metallic sphere where the electric field is 0 inside, but this is not a usual metallic sphere, because you see I am mentioning the charge distribution. So the charge is not on the surface only, it is inside the sphere also, right. So and it is a constant charge density all over the sphere, right, including inside. Now how I will calculate then the electric field? For that we need to use what we discussed in like week 2 lectures, that is Gauss law, right. So first I will take a Gaussian surface, I will assume a Gaussian surface here, right, which is of radius r. Now I will calculate. So Gauss law says that E dot ds is equal to q by epsilon naught, right, where q is the charge enclosed by that Gaussian surface. Now as it is spherical symmetry, this E is constant over the whole surface, where the value of E or the magnitude of E here and here will be same, right. So then I get E integration over ds only, and everywhere E and ds will be like E dot ds direction is same, right. So it will be ultimately cos 0, that is 1. So I can remove the vector sign because electric field and the surface vectors are pointing in the same direction, and then is equal to q enclosed. Now q enclosed, how much charge it is enclosing? That is charge density into its volume. What is the volume of a sphere of radius r? That is 4 pi by 3 r cube, right, 4 pi by 3 r cube, and then you have epsilon naught also here, and ds will be, what is the area of the Gaussian surface here of radius r? That is 4 pi r square. So that is 4 pi r square is equal to this side, let us say 4 pi r square into, I am just writing it in a separate way, right. This is the same, I just taken out 4 pi r square. Now 4 pi r square get cancelled, so magnitude of electric field E is equal to rho r by 3 epsilon naught, right. And now what will be the electric field outside? So while we will take a Gaussian surface for r greater than a, let us say this is the Gaussian surface. In that case the left side will be same, right, because this is E dot ds and E dot ds will give me E into 4 pi r square, that is equals to q by epsilon naught. Now this q, earlier it was 4 pi r cube, but now the r is this much, right, r is greater than a, but the charge is only till a, the total charge is then whatever be my r, now total charge is not dependent on small r, right, it is only the volume of the actual sphere, and that is 4 pi by 3 a cube. So it will become then rho into 4 pi a cube divided by 3 epsilon naught, then E will be 4 pi will get cancelled up, then E will be a cube by 3 epsilon naught into rho by r square. So this is the correct option. Now the next question is that the capacitance of two concentric metal cells with radius a and b, where a is smaller than b. Now for that also we will use the similar integrating equation. Okay, so we know that if we have a two concentric sphere, so these are the two concentric sphere, forgive me for my drawing, this is A, let us say, and this is B, right. Now E is equal to what? E equal to 1 by 4 pi epsilon naught to q by r square, magnitude of E. And we also know that the potential is equals to minus E dot dr, right, integration over E dot dr, because V is defined as E electric field is defined as dV dr, right, and then the potential is integration over the electric field. Now I know that in between any place the electric field is given by this formula 1 by, so let us say this is the radius r, right. So at a position r the electric field is 1 by 4 pi epsilon naught to q by r square, where let us say some plus, if plus q is here, then some minus q charges the outer surface at the outer sphere, right. So because of this charge separation, what potential has been generated? What potential have been generated? So that we are calculating from this integration. So the potential difference between the inner and the outer sphere will be this. So I will just put the, so I am removing the vector signs because E and D are all pointing the same direction, so it will be ultimately cos 0 1. So it is 1 by 4 pi epsilon naught into q by r square dr. Now what is this radius? Radius is from A to B, the potential generated between the inner sphere and the outer sphere, and that inner sphere radius is A and the outer sphere radius is B. So we take 1 by minus of 1 by 4 pi epsilon naught, and 1 by r square becomes minus 1 by r after integration, right, minus 1 by r from A to B. So the negative cancel out, then you get, oh there is this q also, so this is q, right. So minus of q by 4 pi epsilon naught into 1 by b minus 1 by a, right, simple integration. And if you do that, then you will get finally that this is the potential, right, and I have asked about capacitance. So capacitance C equals to what? Q by V. So if you do Q, so Q is there, so if you do Q by V, 4 pi epsilon naught will go on the other side, and then it will be AB divided by B minus A. Sorry, there is one mistake, that is there will be no negative here, because I am taking the chart from the positive side to the negative side. So it will actually the electric field is pointing in this direction, right. So it is ultimately pointing in the same direction, so there will be no negative. This is not 180, this is 0. So this is fine, and then you get, there will be no negative here. So it is minus 1 by r square will become minus 1 by r, and you take the negative out, and then you get 1 by b minus 1 by a, and that will give you this equation. Okay. So this is the correct option. Okay. Next question is, if the plates of a parallel plate capacitor move closer together by a distance delta, then what will be the magnitude of work done in terms of electric field E and the area of the plates A. In the last assignment also we have calculated the force between the two parallel plates, right, and that we know that is ddx of the energy, or let us say if the gap is called r, or then ddr of the energy, and that gives me that, let us say the energy is if the capacitor is CV square, then the energy is half CV square, and then the gap d, so the gap is d also comes down, right, and then C equals to, so this is the force, right, this is the force, then C equals to half into epsilon naught A by d square, and then you have V square. Now you see this is half epsilon naught A into V by d square. Now what is this V by d? V by d is ultimately potential by the distance, so that is my electric field. So I can write it as half of epsilon naught A into E square, right. Now so this is the force, so work done W is equal to force into the displacement, so that is half of epsilon naught E square into A into delta, that is the work done. So this is the correct option. Now the next is for the parallel plate capacitor. So this forces between the, like the normal force and tangential force or the transverse force between two plates of a parallel plate capacitor we have already discussed, and we know that the first option is correct, where the normal force is given by bx epsilon naught epsilon naught v square divided by 2d square, and this is the transverse force, this is b epsilon naught v square by 2d, right. But the second option, for x very greater than d, the transverse force is very greater than a1. This is not right, because normal force, if the whatever be the if the gap is very small between them, then the normal force is much higher than the transverse force. So only one is correct, and these things we have all discussed during the week 2 lectures. Okay. Now this problem where we have two cantilever beams which are moving in plane, means these two beams, this beam will get attracted towards this direction and the other beam will get attracted towards the top direction, right, and we need to calculate the pull-in voltage. Now for pull-in voltage, for the usual case means for a simple cantilever, For a simple cantilever like this, so this is the cross sectional view, okay. For a simple cantilever we have already calculated and we know the formula of pull in voltage, that V pull in is equal to square root of 8k d cube divided by 27 epsilon naught A for a free space, right, there is no dielectric. Now this K is the stiffness constant of the or equivalent stiffness constant of the cantilever, D is the gap between the top plate and the bottom plate, A is the effective area of the two plates, and epsilon naught is the dielectric constant, you know, or permittivity of free space. Now, but this problem is not this simple case, right, because here both the beams are actually moving. Now here are a few things you need to consider. First of all, how these movements are. This movement is actually not even transverse movement, because you see that these forces are distributed, because there is a force acting here also and acting here also, right. So everywhere the forces are acting towards each other. It's like that, right, and there is no force in this region. Like 200 micron is the total length, 120 micron is overlapping, and 80 micron it is not. So that 80 micron there is no force. So it is a distributed load for only a part of the beam, but for simplicity of calculation we will assume that it will be transverse load for the full beam, okay. So for transverse case we already know that the stiffness constant is equal to 3yi by L cube, right, 3yi by L cube. Here now we know y is equal to 120 GPa or 120 into 10 to the power 9 Newton per meter square, right. Then L is given as, here we need to take 200 micron, not 120 micron, because I am considering the whole beam, right, and width is, so W is 2 micron and out of plane thickness is 10 micron, so thickness is 10 micron. Now you see here W is 2 micron, that means this thickness is 2 micron, this width is 2 micron, whereas the thickness is 10 micron. Now this beam is moving in like in the plane, right, in top and bottom direction, like this, as I have drawn here. Now the thing is, then I is usually Wt cube by 12, but here W, the force is acting actually along W only, so it is T W cube by 12, okay. So I equal to T W cube by 12, and then you get the KT is equals to, if you put all these values, then you get the KT value equals to 0.4 Newton per meter. Now the point is, but after doing that also we cannot apply this formula, because both the beams are moving. Now what we can do here is, we can consider one of the beam to be stationary. Let us say I consider this beam, that is the bottom beam, to be fixed. Now if the bottom beam is fixed, then to make the displacement same, the top beam have to move by double the distance, because see, if both the beams move by, let us say 10 nanometer towards each other, then ultimately the relative displacement decreases by 20 nanometer, right. And while I am considering that one of the beam is fixed, then I need to make such an arrangement so that the top beam will move 20 nanometer. And how that is possible? That is possible if we consider the effective stiffness K effective to be half. So that is equals to 0.2 Newton per meter. So x equals to F by k, right. So if we make the k half, then we are actually making the displacement as twice, which is required while we are considering one of the beam as fixed. Now why we are considering one of the beam fixed? Because if we consider one of the beam fixed, then it becomes like our usual case. It becomes like our usual case where we can consider the bottom plate is fixed and the top plate is also moving, or top plate is only moving. So in that case we can directly use this formula that V pull in is equals to square root of 8 k, so this will be k effective d cube by 27 epsilon naught a. Now this a is the area, that is 120 into what is the in plane, what is out of the plane with thickness, that is 10 micron. So into 10, so 120 into 10 micrometer square, right. So there will be 10 to the power minus 6 into 10 to the power minus 6, 10 to the power minus 12 coming out of this, okay. So this is A, and then you know D equal to 4 micron, and you already know K effective to be 0.2 Newton per meter, right, and epsilon naught is anyway known. So if you put all these values and calculate, you will get 18.8 volt. So mind it that we are after calculation we are getting one value, but while accepting the answer we have kept a range, so that because of these decimal points, your answers correction will not be affected. The next question is electric energy density of a parallel plate capacitor if the electric field inside is E, right. Now what is the energy U? U equals to half C V square, right. Now C equals to, okay, let us say C equals to epsilon naught A by D, and again V equals to what? V equals to, as I wrote earlier, E into D, E into D whole square, right. So can write it as half into epsilon naught E square into A into D. Now A into D is the volume of the capacitor, right. This is the volume of the capacitor. So the energy density is U by AD equals to half epsilon naught to E square. So this is the correct answer. Now this question is also similar to the question number I guess 6, right. So there we have to just equate between the electric force and mechanical force. Earlier we have actually, so this is in lecture 2, in week 2 we have already we have discussed about the COM actuator, and there we have used this formula, or we have derived and also discussed this formula. It is the electrostatic force for this kind of COM actuator was given by N B epsilon R epsilon naught divided by D into V square, where V is the applied voltage and N is the number of combs present on the dynamic mass or the proof mass. So proof mass, like here, is having ultimately 3 combs on each side, so total 6 combs. But in this case, as I have mentioned, that C1 is not connected to the circuit, so ultimately we have to consider only 3 combs, right. B is the breadth and D is the gap between the combs, right, and V is the applied potential. So this is the electric force and electrostatic force. And what is the elastic force? Elastic force is Kx, we know, but then we need to calculate the effective stiffness constant, and for that you see that this is connected like a crab leg arrangement, where we have 4 legs, right, and all of these legs are in guided beam kind of motion, because this region also will not have any slope, and here also it cannot have any non-zero slope. So both the cases, all the beams, it is guided beam. Now in practical case there will be some deflection or axial stress on the AB part also, but for the simplicity we are not considering the AB part now. So let us say only the longer part or the thinner beam if we consider, then we can write that for guided beam we know that Kg is equals to 12 Yi by L cube. Now here also again you need to consider, you need to be careful about what is your width and what is your height. So again the beam is moving, the deflection or the movement is in this direction, right. So this is each of the squares, as I have mentioned, each of the grid is 5 micron. So here this in plane width is ultimately for this kind of force is the height, right. So I is equal to H W cube by 12, where W is equal to 5 micron and H is equals to 25 micron, which is the actual thickness or out of the plane thickness. And if we do that, then we will get the, if we put all these values, and L we already know, L if you calculate that there are 13 squares, so it will become L is equal to, will become 13 into 5, that is 65 micrometer, and if you put all those values then you will get K equals to 1923.1 Newton per meter. Now there are 4 beams, right, 4 beams, so the, and all the beams are in parallel because it is the same deflection for all the beams. So K equivalent is equal to 4 into kg, 4 into kg. Now I know the electric field also because F E equals to, I have already put the formula here, right, and where N equals to 3, B is similar to the H here, right. So B is 25 micrometer, epsilon r is 1, epsilon naught is already epsilon naught you know, right, 8.85 into 10 to the minus 12, and then you D is the gap between the comb, and that is also 5 micron. So 5 micron. Now then you will get the you will get this expression, right. And so what is the mechanical force? Mechanical force is K equivalent into the displacement, and displacement is let us say y, where y is equals to 5 nanometer, y equals to 5 nanometer. Then if we put all these values together, then we will get that and then you can calculate V will be equivalent to equal to 538.3 volt. So you just put all the values and calculate, it will come as 538.3. And I hope that you understood here that we are applying the ultimately the mechanical force and electric force will be same. So that fact we are applying here. So this is the electric force and this is the mechanical force, and mechanical force is equal to Kx, and that is my K equivalent into y or the displacement, right. Our displacement is 5 nanometer and K equivalent is equal to 4 times of the each of the stiffness constant of each of the beam. So accordingly we are getting this expression, and this side we have already discussed during the lecture videos. The next question is, which of the following process will not avoid friction? So fabricating a stiff cantilever, using wider beam, using methanol. So methanol definitely avoids friction, then making narrow dimples also will avoid friction. Stiff cantilever will also reduce the possibility of friction, but wider beam will not make the stiption lesser, because as we are making, if a beam is made wider, then at the same time, let us say this is the fixed position, then the whatever droplets is made here, that contact area also increases. So it is ultimately the water droplet form that is also bigger because of the wider beam. So it will not help really in stiction. Which of the following should not be used for either sublimation or supercritical drying? So liquid CO2, you know that we use for supercritical drying, dichlorobenzene is used for sublimation, and liquid butyl alcohol is also used for sublimation, but DI water is the only material here which does not help in sublimation or supercritical drying. And you need to understand here one thing, that DI water we don't put DI water in the during the lectures videos. You have seen that DI water was present while discussing the sublimation or the supercritical drying also, but that is not because DI water is needed for the sublimation or supercritical drying. Okay, you need to understand this point, that DI water is required for our usual fabrication process. Okay, so while we are doing fabrication, let us say etching or lithography, lift off, so in those steps DI water is used. So ultimately after completing those steps, our samples are inside that DI water, because we have used the DI water to clean the sample. Now while we take out the sample from the water, there is this possibility of stiction. So our whole aim is to remove DI water without making the beam stuck to the substrate. So that's why we use liquid CO2 or dichlorobenzene or butyl alcohol, and water actually helps in stiction. So it will not be helpful for sublimation or supercritical drying or in anything, right? Because this is not the agent for sublimation or supercritical drying. This is there because we get the sample from our last etching step or lift off step, like that the sample is submerged into the DI water. So we cannot help that. We are not using DI water for supercritical drying or sublimation. So you need to be very careful about that, because I think some of you have confused that DI water is also used for sublimation and supercritical drying, which is not true. DI water comes from the etching steps before. We start with DI water because the sample was already inside DI water. Now our goal is to use sublimation or supercritical drying or some other technique so that it will not get stuck. So this is the correct answer. So I hope that you have understood assignment 1 and 2 both. So thank you.